Okay, Joseph Palmer, thank you for joining us. You'll be talking about extending circle actions to integrable systems.
Okay, great. So yeah, first of all, of course, thanks for the invitation. It's I know it's great to be involved with this conference. I can be honest though and say I've been asleep during all of the talks, but I'm looking forward to watching the videos. So the abstract sounded good, I guess I can say. But yes, so I mean, this talk, it's joined with Sonia Holak, and it's really just about the relationship between Hamiltonian circle actions on four manifolds and integrable systems on four manifolds. So this is sort of the idea. And right, if you're on four manifolds, an integrable system is just two functions. And so assuming that one of your functions generates a circle action, a Hamiltonian circle action, then it's just the difference of this additional function that you can either forget to recover the S1 space, or you can try and find to sort of boost the S1 space up to being an integrable system. And then there's lots of questions you can ask. Some of these questions were answered a long time ago. Some of these questions were answered a little while ago. And some of these questions are sort of new. So for instance, you can ask for which, and I'll define all these things in a minute, but I assume that people who are at this conference probably know what they mean. But anyway, for which S1 space can we find a Hamiltonian so that it lifts to a toric integrable system? It's a totally natural question. But you can ask the same question for instance, what are called Semitorque integrable systems. I know Alvaro talked about these, Alvaro Playa talked about these on the first day. And you can even ask this in more generality. Other integrable systems where one of the integrals is assumed to be periodic, you can say, given S1 space, does it automatically lift to an integrable system at all? And then if it does lift, kind of what can we say about its properties or the form that it's in, things like this. And this is sort of the reasoning behind this whole project, I guess. Okay, so maybe I'll define things now. So for this whole talk, M omega is going to be a four-dimensional compact symplectic manifold. These questions make sense, and some of them have answers or partial answers or whatever in higher dimensions or a non-compact. But for today, this is just what we'll talk about. Okay, so any function on a symplectic manifold induces a Hamiltonian vector field. We know this. And yeah, if this Hamiltonian vector field, if it has flow which is periodic, we say that function generates an S1 action, right? This is the same as saying we have a Hamiltonian S1 action, except instead of talking about the momentum map as a map into the dually algebra, I'm just taking it into R. And I'll assume everything, when I say periodic, I'll always mean period 2 pi for today as well. Okay, so one of our objects of interest is a Hamiltonian S1 space. So this is just going to be a triple M omega J. M omega is going to be a symplectic manifold, and J is going to be the Hamiltonian. And it's going to generate an effective S1 action. And these were classified by Yael Karshan in this great paper that she has in 1999 that I'll talk about a lot today, by these things called Karshan graphs. And this is an example of what a Karshan graph looks like. You have some vertices and you have labeled edges, and some of the vertices are fat. Yeah. Oh, right. And so now I can explain those a little bit better. But again, probably a lot of the people here are pretty comfortable with this. Essentially, the idea is you take each interesting feature of the S1 space and you encode it as some part of the graph. So an isolated fixed point of the S1 space is represented by a vertex of the graph. It turns out the only other configuration that fixed points can arise in this scenario is a surface. So a fixed surface of the S1 space is going to be correspond to what's called a fat vertex of the graph. So it will have, it'll be drawn like an oval like this, and it'll be labeled by the volume of the surface and the genus of the surface. And the only other sort of interesting thing that can occur from the sort of group action point of view is points with some non-trivial isotropy. And it turns out in these S1 spaces, these always arise in spheres. So you have this S1 action that, everything should return to itself after, time 2 pi. But there's spheres of points that sort of rotate k times too fast. So after time 2 pi, this sphere will have rotated k times. And sort of the interesting thing to notice here is that if you have a sphere that's rotating, then its endpoints are fixed points. And so it makes sense to have the spheres, the zk spheres, represented by edges, because they connect fixed points, they connect the vertices. And the other thing to say is that all of the vertices are labeled by sort of where they are in terms of the value of the momentum map. So they'll be labeled with their J value. And so a picture of a Gaussian graph might look something like this, where I'm taking the left and right direction to describe the J value. Right. So this is sort of one object. These are S1 spaces and they're Gaussian graphs. And then sort of the other object for us is going to be a 4-dimensional integrable system. So we again have a symplectic manifold M omega, but now we have 2 functions, J and H, such that they Poisson commute and they're linearly independent everywhere. And if I want to start with sort of the simplest, nicest, and of course from sort of momentum polytope point of view, most natural examples, these are toric integrable systems. So you can think of these as a Hamiltonian torus action. That's a totally natural way to think about it. But for us, I'm going to think about it rather as 2 S1 actions. J generates an S1 action and H generates an S1 action, because this makes the relationship to S1 manifolds even easier. And as we know, it's sort of the point of this conference. These are classified by their moment image, which is a polygon, right? I'm doing 4-dimensional systems, so I don't have to say polytope. I can say polygon. And here is sort of a slide about that, but this is known to us. The Tia Gilman, Sternberg, and Delzant results all together form this bijection between toric systems and Delzant's polygons, which are their image. And something that, again, I think is known, but I should say, just because it's how I'm going to prefer to think about these things, is we can look at the fibers of this map, right? We have this map that takes, in this example, CP2 to the right triangle. The preimage of interior points, I'll call these regular fibers, they're tori. The preimage of points on the faces are circles, and the preimage of points on the corners are isolated points. So as we get to more complicated integrable systems, I'll still describe them like this, just talk about the fibers mostly. Okay, so here's sort of our game plan in the toric case. You can start with a toric integrable system, since both of the functions generate an S1 action. If you just delete one of them, you're left with a Hamiltonian S1 space. And so you can start with a polytope. So for instance, this is the second Hirzebερg surface blown up one time. And you can draw the graph from that. And this is all still due to Karshan's paper that I was talking about earlier. And then something that's also very interesting, which is also still due to Karshan's paper, at least in the toric case, is really being able to go back and forth. So if you start with a Hamiltonian S1 space, can you find an additional function to lift it to a toric integrable system? That's sort of this right to left arrow. So really the best way to do this is, instead of thinking specifically about these objects, we can think about their invariants. We want to look at correspondences between Delzant polygons and Karshan graphs. So here's a dictionary for that. So any vertex of the Delzant polygon for M omega JH corresponds to a vertex of the graph for M omega J. And so I have these sort of highlighted here, except this first line doesn't include vertices that are on a vertical wall, because vertical edges of the polygon correspond to fat vertices. They're all spheres in a toric system, and their area is related to the length. There should be a factor of 2 pi. And then the other thing are the ZK spheres. and the zk spheres come from edges that have slope a over k, where a and k are relatively prime integers. So this is supposed to be slope minus 1/2, and therefore it corresponds to an edge with a label 2. And so what happens is these other edges that have integer slope correspond to sort of a Z1 sphere, which isn't special at all, right? I mean, it's supposed to take one period for a point to return to itself. So a Z1 sphere is sort of a free sphere, and so they don't show up on the graph. So all of these integer slope edges just disappear. Okay, so this is sort of the plan, and I'm going to jump into an example that I'll sort of follow for the rest of the talk. So let's start with CP2, and from here we can take, here we have a vertical edge that becomes a fixed, there's a fixed sphere, so it corresponds to the Cauchy graph. It has a fat vertex. Here we have two edges that have integer slope, so they just disappear. And here we have a vertex on the right, so it becomes an isolated fixed point. And now what I want to do is just start taking some blowups of CP2. So we can take blowups of the Delson polygon by doing corner chops. So let's do a corner chop on the top corner. And again, you can draw the Cauchy graph. All of the slopes are still integer, so they don't show up as edges. We have a vertex and a fat vertex. And so, so we get this picture. And I'm making my fat vertex a little bit less fat as we go along, kind of indicating the area without having to label it. And then we can go again. You can let's do a blow up of the same size on that fixed surface again, which is perfectly fine. And now we have two vertices that have the same J value on the graph, so I can just draw them over each other. And the point now is that, well, you're probably pretty comfortable with doing blowups on a Delson polygon, but there's also rules to do blowups on Cauchy graphs. I won't explicitly state them, but the point is that what we've been doing, we can do again. You can make this fat vertex smaller at the cost of adding an extra isolated vertex in the graph. And if I want to, I can add it at the same J value. So there's some rules for this, and if we do this, we can get a graph like this. And sort of the takeaway here, this is maybe one of the kind of key insights. If you think back about the dictionary corresponding features of the S1, or features of the graph and features of the Delson polygon, everything in the graph came from the boundary of the polygon, right? It was the slope of an edge, or it was a vertex, or whatever. And so if you have three of anything on top of each other, like here we have three fixed points, all at the same J value, this is never going to be able to come from a Delson polygon, right? Because one of those dots comes from a corner on the top boundary. The other of those dots comes from a corner on the bottom boundary. And then there's another dot, and there's no more boundary that could come from. And so, so this Cauchy graph is an example of an S1 space that cannot come from a toric system. Right, so that's sort of one of the main ideas, because we're going to come back to it again in a slightly more complicated situation. But this talk, or this project, is about trying to extend these S1 spaces to integrable systems. So let's see what we can do. Okay, we can't extend it to a toric system, but maybe we need to go beyond toric systems. And so the next, a very natural next step are these semitoric systems. So this is, I know Alvaro talked about this in the first talk. A semitoric integrable system is an integrable system M omega JH, such that J generates an S1 action, but H doesn't. H is more or less, is really much more free. The only condition on H is that the singular points of the momentum map are what are called non-degenerate, and they don't have what are called hyperbolic components. So I will talk about that right now, just briefly. This comes from, I mean, it's sort of the analog. There's a thing like the Morse lemma in integral systems, that there's a sense of which points are non-degenerate. And if you have a non-degenerate point, there's something like the Morse index, which is sort of this classification of what the points look like locally. And it's called Eliason's theorem because Eliason had it in his, stated in his thesis and proved some of it in his thesis. But there were some gaps, and many people have filled those gaps over the years. Eva Miranda, who is here, and Zung, and Sanbu Ngak, and Wisho. So the gaps have all been filled, but it's I don't know. I mean, it's not giving all the right people credit to just call it aliasance theorem, I guess. Anyway, so that's one note. Another note is that semitoric integral systems are important for various reasons, but one of the reasons is that they're classified, like toric systems are classified, except it's more complicated. And this is by Plyo and Vunagak in terms of 5 invariants about 10 years ago. And one of the invariants is a polygon. And then the other invariants are some dynamical things that I don't have time to go into. I could talk about it. I could easily do a whole talk about it. And the other thing I should mention about this is that since J generates an S1 action, we can still do the same trick we were doing with toric systems. If you just forget the function H, now you have an S1 space. And conversely, if you start with an S1 space, you can try to find a function H to lift it to a semitoric system. So now we can sort of play with all the same questions. And let me do sort of one more slide about semitoric systems in general. So the image of the momentum map of a semitoric system is not going to be a polygon. It will be some shape, and I've marked sort of with an X a special point in the interior, which will behave a little bit differently. If you stay away from the special point, the fibers look like the toric fibers. The interior tori, the faces are circles, and you still have kind of, it's like a curvilinear polygon, I guess. You still have kind of corners, and those are elliptic. But there's some finite number of points in the interior where their fiber is a pinch torus. Sort of one of the cycles of the torus is collapsed as you got close to that. And these are called focus fibers. And these fibers don't admit a T2 action, but they do still admit an S1 action that sort of rotates them like this arrow says, like this. And what's interesting for us and for this talk is that that means the pinch point, which is the focus point itself, is a fixed point of the S1 action. And I'll come back to this in a minute, but this is just giving us a new place where we can encode, or we can sort of hide isolated fixed points of the S1 action in the interior of the momentum map image. And another thing I should mention, because it's important, and also because I should stay at least a little bit on topic for this conference, is that this image f of m isn't given to you as a polygon, but it still sort of secretly has the structure of one almost. The point being that this torus vibration over the regular fibers gives you an affine structure. And it just doesn't agree with the affine structure of R2, which is why you can't see that it's a polygon. Whereas in the toric case, that's essentially what happens. And you can't really make it agree with the affine structure of R2. You can't make these edges look straight, even though they should be straight, because there's monodromy around the focus point. But there's a clever fix for this, which is something that Sanbu Ngak came up with, and independently Margaret Symington came up with, which is you just cut out that point. So you choose a cut direction from the focus point, either up or down, and you draw a ray coming out of that point, and you remove its pre-image. And the point is that now you're left with a simply connected region of regular points, which means monodromy can't exist, which means you can straighten out the image. And so I've said a lot of things very quickly if you haven't seen this before. But the point is that you can take this image and you can turn it into a polygon that's similar to a Delzon polygon, but more complicated, which is really interesting and called a semitoric polygon. So, right, but now getting back to sort of the reason I'm interested in them at the moment is that these are kind of like Delzon polygons, but these marked points in the interior, which correspond to pinched tori, give us fixed points of the S1 action in the interior. And so this polygon that I've drawn here, if you forget the value of H, you get an S1 space that is the one we had before. The S1 space is this one that has 3 fixed points all on top of each other that couldn't be lifted to a toric system. So this sort of moves us forward towards getting more S1 spaces that can be lifted to these integrable systems. And There's several papers. I've even only listed 2, but I guess there's at least one more about the relationship between Semitorque systems and S1 spaces. First in 2015, Holak, Sabatini, and Seppi talked about how to get from the polygon to the graph. It's completely analogous to the Delzant case. And then Holak, Sabatini, Seppi, and Symington have sort of an ongoing project about going the other way and about really understanding this relationship back and forth between these two pictures. Right. So let's. I want to go further than this though, because let's notice something. So again, I haven't told you the rules for doing blowups, but you can do a blowup at an isolated point in a Cauchy graph, and you can get like a little Z2 sphere like this. So if I do 2 more blowups, I still have a totally valid S1 space. This is now CP2 blown up 5 times, and it has this picture. And if you're very careful and you take 20 minutes, you can draw this Semitorque polygon that corresponds to that graph. You have sort of a Z2 sphere on top. The cut runs into the Z2 sphere, which is fine because the cut is really of our own invention. It doesn't really mean anything is running into each other. You have a focus point. You have another Z2 sphere down here, and you get this picture. But let's do a blow up again, and then let's hesitate, although it's already 20 after the hour, so let's not hesitate too much, but let's hesitate and look at this. Because the same thing that happened in the Torque case is happening again. Now, with Semitorque systems, you can fit isolated fixed points into the interior. And so you can have lots and lots of isolated fixed points on top of each other in the Cauchy graph. But if you think about it, the ZK spheres still have to come from either the top or bottom boundary of the system. And so having 3 ZK spheres at the same level of J is never going to work, because one of them comes from the top boundary and one of them comes from the bottom boundary. And then the third one has nowhere to come from. So this S1 space cannot come from a Semitorque system. And so this is why I want to push even further beyond Semitorque systems to a larger class of integrable systems in order to find a system that this can extend to. I guess that's sort of the point. And let me sort of briefly explain the new points, the new fibers at least, that are going to show up in the systems I'm going to talk about. So here we have the fibers we've talked about so far, the ones that show up in toric systems and the focus fibers. And here's a new fiber I'll talk about, a hyperbolic regular fiber, which is really just 2 tori that are like sitting exactly on top of each other. So it looks like a figure 8 across S1. And I should mention in the systems I'm about to talk about, hyperbolic elliptic point, rather fiber, and hyperbolic points can't occur in the presence of a S1 action anyway. But the point is that I'm going to allow all of the non-degenerate fibers that can possibly occur with an S1 action. But actually, it will turn out that this is not enough. And there's one further type of point, which is actually degenerate, that naturally shows up when you have hyperbolic regular points. Not all the time, but very frequently, which is called a parabolic point. And it's what occurs when you have a hyperbolic regular point that collides with an elliptic regular point. So hyperbolic regular points come in 1-parameter families, and elliptic regular points do too. And when they collide, you can sort of think of this as you have your figure 8, one of the tori is shrinking. And so the top torus becomes a circle and becomes sort of a singular circle on top of a torus. This is like a cuspidal torus, I guess I should call it. And this has a lot to do with the fact that in toric and semitoric systems, this doesn't show up. But in if you're allowing hyperbolic regular points, very frequently you're going to have disconnected fibers. Some fibers of your momentum map are going to correspond to 2 different disjoint tori. And parabolic points are interesting for various reasons. There's relatively recent papers by Bolsanov, Glemy, and Krzyzewska, and Astafiou and Guy Kobe that, first of all, talk about the symplectic invariants, which are extremely interesting in this case, because there's more going on than in the non-degenerate case. And Astafiou and Guy Kobe's paper, they talk about flaps. And so these parabolic points often come in a configuration where they're like in a pair, and they're connected by hyperbolic regular points, and they form a flap on your momentum map. So I'm a little tight on time, but I'll show these fibers quickly, and then we can get to the result. So this is what the momentum map image will look like when you have a flap. And you sort of want to think of this image as that triangle is glued on along the red line, and then it's like hanging off. There's like a triangle just hanging there. Because you'll see that inside of the triangle, we have disconnected fibers. So it makes sense to think of it as like two sheets. And outside of the triangle, we'll have connected fibers. So outside of the triangle, our fibers are the usual ones. Corners are points, edges are circles, interior points are tori. And as you get closer to the hyperbolic regular point, this tori will sort of separate and then pinch at the hyperbolic regular point and then split into two fibers. So that's why you have these disconnected fibers inside of the flap. And then once you get to the flap, you sort of have two distinct things going on at the same time. Downstairs, you just have regular tori, and upstairs, you have something that looks like the corner of a momentum map. One of the tori will degenerate into a circle along these curves and to a point along, at this edge here. So you really have something that looks like the corner of a momentum map upstairs, and in parallel, you have sort of regular, non-interesting points. And then these edges are the parabolic points. Okay, so why do we care about this configuration? Well, because of what I just said, that the flap looks like a corner of a momentum map, and therefore you can do a blow up there, right? There's an elliptic point. You can do a corner chop, and what that does is it lets you do a blow up and get, this is here a Z2 sphere in the interior of the momentum map image. So going back, remember our whole problem was that in Semitorque systems, the ZK spheres could only come from the top or bottom boundary. But this is giving me a way to get a ZK sphere that comes from the interior, and therefore giving some strategy to have three ZK spheres all sort of on top of each other. So hopefully that makes sense. I will sort of show it in the example we've been returning to. Here is the system that could be lifted to a Semitorque system. I could draw a polygon, but I'll just draw the actual momentum map image. It's a bit curvy. And now I'm going to very quickly do a trick, which is let's take this focus point. I don't want a focus point. I want a flap. Well, conveniently, there's a paper about exactly that by Holger Dulin and Oliver Playa, who also both spoke at this conference. That gives you a way to turn a focus point into a very small flap via the Hamiltonian-Hopf bifurcation, and it doesn't change the symplectic manifold or the S1 action, which is to say it doesn't change the Karchan graph of the underlying S1 action. But now we're in a scenario in the integrable system where we can do a blow up, and that will correspond to the blow up that we couldn't do before, that we couldn't do and keep inside of a Semitorque system. And so this essentially gives us a way to carry along the integrable system when we perform blowups at focus points. And you can sort of, I mean, this is kind of the key insight. I've skipped lots and lots, but this is what sort of takes us to our result, to my result with Sonia, which is that if you start with any compact four-dimensional S1 space, then you can always find an additional function such that m omega jh, first of all, is an integrable system, and furthermore, all of the singular points of the system are either non-degenerate or some of them are these parabolic points, which I should mention. The parabolic points are, I mean, they're sort of thought of as the most well-behaved degenerate points. So the fact that their symplectic invariants are understood is sort of a little bit of evidence towards that. And I should mention that this result is somehow sharp in the sense that there are some systems that need some kind of degenerate point, and so allowing the nicest possible degenerate point is sort of the best you can do, I guess. Oh, right, and we gave these names, we gave these systems a special name, which is hypersemitoric. So if you want, I can say that any four-dimensional S1 space can be lifted to a hypersemitoric system, which is what I have here. But this is, I mean, this is the same theorem. I just added in the sort of jargon, I guess. Well, it's 8:29, but I'm going to take 30 seconds to tell you the idea of the proof, because it really does only take 30 seconds. There's really three steps. You start with any S1 space. Due to Karshan, that S1 space comes from some minimal S1 space that she lists out more or less explicitly. You start with one of these minimal spaces. If you do a bunch of S1 equivariant blowups, you can get the space you're interested in. And it doesn't take too much effort, medium amount of effort, to check that all of the minimal spaces admit one of these hypersemitoric systems. And then all you have to do is say that if you start with a minimal hypersemitoric system, you can carry it along by making flaps and doing things like we were saying before to an integrable system on the S1 space that you're interested in. And this is really the difficulty of the paper. I mean, you have to be extremely careful about the sizes of the flaps and making sure you can do lots of blowups on the right flaps, so the flaps don't run into each other. I mean, I don't know, it was very delicate, but the idea, I think, is very clear. Minimal spaces can be lifted to hypersemitoric systems, and then you just carry that along through the blowups to get all spaces can be lifted to hypersemitoric systems. And here's the same theorem again. Yeah, so thank you for listening. That's all I have.
Thank you very much, Joseph. That was excellent. That was really, yeah, fascinating. If does anyone have any questions? You're getting a lot of claps. I hope you can see that.
Yeah, I see one or two claps.
Does anyone have any questions? I personally have a question. I was wondering about, I don't know if anyone's raised the hand or anything. I have a question. There was something that I came across recently, maybe that's a bit late, but about blowdowns. Mm-hmm. And I was wondering if this applied.
Yeah, I mean, I guess the blowups are sort of easy to describe. This is always how it kind of works, right? You have essentially the blowup says something like you look for an embedded, symplectically embedded sphere, and maybe it respects whatever group action you care about, and you try and remove that sphere and collapse the boundary, and so that's sort of okay. And the blowdown is just going the other direction. I guess you have to kind of understand the blowdown to find the minimal systems, right? The minimal systems are the ones that don't admit any blowdowns. And so an equivalent way to state this minimal model idea is you can start with any S1 space, and you can just keep doing blowdowns on it until you can't do it anymore. And then it must be a system that doesn't emit blowdowns. And if you've classified them, which is what Karshan has done here, and other people have done in various other scenarios, then you sort of know what kind of space you have to land on. And then, yeah, her classification of these minimal spaces is sort of what lets us, well, I mean, then you just have to understand those minimal spaces, I guess what I mean, which there's toric ones, and there's some that are ruled surfaces and things like this. And then you just undo all the blowdowns that you did to get back up to the space that you started on. I hope that makes sense. It's sort of a typical trick, huh?
No, sorry. So you're saying that because you kind of you stick to the minimal space, right? Mm-hmm. The minimal S1. So therefore, blowdowns, you can't perform them. Did you say that? Or yeah.
So the point is that so for instance, even the example that I did today, I started with CP2 and I did 6 blowups on it to get some space whose Karshan graph looks like this. But sort of the point of the proof is you have to go the opposite way, right? I have to hand you this graph and say, hey, can you put an integrable system on this? So then what you have to know is you need to be able to look at this graph, and you need to say, okay, I'm going to just do blow downs on this as much as I can. So all of these two spheres will become isolated points, and all the isolated points will disappear, and the fixed surface will get large. And the point is that then you'll end up with CP2. And you know that CP2 admits a toric lift. And then you do what I did in the talk, which is you start doing these blowups one at a time and pulling the integrable system along with you at each step. And possibly to do one of the blowups, you need to create a flap, which is like what we needed to do, or you have to do, I mean, there's sort of various types of blowups that need to occur, I guess. But yeah, this is, I mean, yeah, this is the strategy. And it isn't quite as easy as just doing induction. It's just saying, okay, here's some integrable system. If I do a blowup, I can still put an integrable system because all of the blowups need to be done sort of coherently with each other. I mean, otherwise the flaps end up on top of each other and it gets complicated, I guess. I don't know. I mean, maybe I'm emphasizing this too much, but I was stuck for so long about the size of the flaps. I mean, months and months. So I don't know, it was hard. But yeah, that's sort of the idea. Does that make sense?
Yeah, no, it does. What was the breakthrough with the flaps? Sorry, I know.
Oh, no, it's, I mean,
for you personally, I mean.
Yeah. So for me, I guess the point is that if you do, so for instance, in this space, if you do symplectic reduction at any of these levels of J, you always get a sphere. And you can think about the H, this other functions you'd like to find, as a sort of a family of functions on the sphere. You know, you choose a level of J that gives you a sphere, and then on that sphere you choose usually a Morse function, and that if you have a family of Morse functions, you can like lift them to the integrable system. It's not quite like that because all of these singular points, or I mean, all of these fixed points of J will turn into singular points of the sphere. So your sphere will be shaped like a teardrop or like a lemon or whatever. And when you understand it like that, these flaps become points where your sphere has like a, I mean, it's like one of the typical Morse functions on the sphere. If I had a chalkboard, it's like a sphere with like two humps, you know, and the hyperbolic regular points come from the index 1 point on the sphere, you know, because they're a figure 8 is the level set on the sphere, and so when you cross that with S1, you get the double torus.
Sure.
And so sort of when you understand going from left to right as starting with a sphere, making like a hyperbolic point, and then getting rid of that hyperbolic point, you can reframe this question about the sizes of the flaps into a question about, I mean, really a question about families of Morse functions. And to get the non-degenerate points upstairs, you want Morse points downstairs. And to get the parabolic points, there's sort of a typical bifurcation that happens in Morse theory, where like index 0 and an index 1 point collide and disappear. It would really, it's like you have like this bump hanging off the sphere that then like goes away. And there's something called surf theory, which I learned about during this project. Maybe people know more about it. That's really about exactly these sorts of things, transformations of families of Morse functions going through certain bifurcations. And it turns out the sort of typical thing that happens in surf theory downstairs corresponds to parabolic points upstairs. So it takes some effort to sort of get everything in correspondence. But once you understand how to do everything in terms of more or less Morse functions on the sphere, then there's still some work, but it became much more tractable to me, I guess. That was a long answer to your question, I'm sorry. But,
no, it was, no, thank you so much for the thoroughness, really.
And then I think this is the right way to think about these systems in terms of looking at the parameter of the family of reduced spaces, I guess.
Oh, yeah. Does anyone else have any questions?
Hey, Joey.
Did I hear something? Yeah.
Oh, yeah.
I have a question.
Zuti.
Yeah.
Hey, Joey. It's very interesting. You invented the hyper Semitorque systems. So have you thought about any possible polygon classification theory of this?
Oh yeah, well this is a totally natural question. Of course, as soon as we were coming up with a new class of integrable systems, I'm thinking, classifications are really nice. You know, the classification of Semitorque systems, of course, is like this great result that's extremely useful. So yeah, I mean, if you're thinking about classification questions for hypersemitoric systems, you just need to look at Alvaro and San's papers and say like, okay, what can we use and what do we need to adapt? So, I mean, I mentioned that that Bolsonov and some of his co-authors were able to describe symplectic invariance of the parabolic points, so that's useful.
Oh, nice.
And yeah, and then you just need to sort of understand these flaps. And I think a natural thing to do is to sort of cut the polygon along the hyperbolic regular points, like cut the flaps off, you know, and then the flap becomes a polygon, and the polygon itself, or I mean, the rest of the momentum map becomes a polygon, and then you sort of will have this like complex of polygons to glue together, something like that. I mean, yeah, it's kind of fun to think about. I think it can be in principle quite complicated, but it's looking a bit ahead. I think something like this would be doable, or at least defining a polygon invariant. Then this talk would fit to this conference even better. If the hypersemitoric systems had a moment polygon too. Yeah, and you can think about Taylor series invariants and things like. Oh, sorry, go ahead.
What kind of a symplectic invariance you find for the parabolic points? Is that are those the local invariants or semi-local invariants?
They're both. So I mean, the non-degenerate points don't have any local invariance, but the parabolic points do. They have a local normal form, but it's only a smooth local normal form, so it doesn't take into account the symplectic structure. And so there's lots more invariants that come from that. And then you can sort of take that invariant and transport it along the whole orbit, and it's okay. And I'm pretty sure these things also, if you define everything right, come from the affine structure, like the other invariants do. So it fits a little bit into this picture. But then, I mean, you write it. I mean, you know the Semitorque classification. So if you spend an hour thinking about it, you'll think, oh, I need like a family of height invariants for the curve of hyperbolic regular points, and you need to know the volumes of all the different things, and then there'll be you can have focus points on the flap and things. I mean, all sorts of these pieces can combine in interesting ways. But I mean, there's some breakthroughs, I guess, still needed, but a lot of the foundational stuff is really there, I guess. Yeah, so it's an interesting question. Of course, I've been thinking about it. It would be great to classify these things.
Also, for the flaps, you mean the flap is along the curve, and is there any restrictions on the curve?
It seems, I mean, the curve can't be, it can't have any vertical tangencies. And this was something that was conjectured by Doolin and Plyo in their paper, that you can't really have like a circle of hyperbolic regular points, and the reason for that is because you can't have vertical tangencies. But other than that, the curve can sort of do whatever. And incidentally, the fact that you can't have vertical tangencies sort of is why we need these parabolic points so frequently. Because this curve of hyperbolic regular points, it can't connect to itself. It has to end somewhere.
Yeah.
And it can only end, either it can end in a fixed surface, or it can end in a parabolic point. So if you don't have any fixed surfaces, or you don't have two fixed surfaces, that's when you need these parabolic points to be there. That's kind of an aside.
Wow. That's interesting. That's very interesting. For the hyperbolic regular points, I thought that this the hyperbolic regular point, the classification around that is not easy because the fiber are not locally connected, right? So how do you overcome this?
Yeah. I mean, I don't know how I would overcome this. But yeah, because you get these. I mean, it's the point where the fibers break into pieces. So probably. I I mean, it would be something, I mean, I say the affine structure. I don't really mean the affine structure on the moment image. I mean the affine structure on the base of the fibration. So you'll have like two levels during the flat that will have two different structures, right? I mean, this is one of the things that's so great about semi-torque systems is since the fibers are connected in torque systems, the moment image is the base space of the vibration. So you can go right back and forth between these two worlds really easily.
Yeah.
And this is, I think this is why people were kind of staying away from hyperbolic regular points. But I don't know. I think it's interesting. I don't know. Maybe it's a bad idea.
You need like two-step classification. First, on the level of the base space, and then from the base space to the momentum map image.
Yeah, something like this. Well, and this is why these like sort of quantum questions are harder too. That the spectrum really is in the moment image, not in the base, and so you have like two spectra on top of each other. This is completely aside from my talk.
Oh, wow.
But you can do, Johan LeFloc tells me you can do some trickery, and if you have two spectra on top of each other, you can tell them apart. But I don't know. I don't know how you could do that. It just looks like a bunch of dots to me. But he knows what to do. So yeah, there's a lot. I mean, it's this project opens up millions of questions, I guess, and this is what I kind of like.
All right. Thank you very much. Thanks a lot.
Thank you.
Joseph, really.
Yeah. Thanks.
And that was an excellent talk and discussion.